Okay, can you see the screen? Okay. So Susan, can you hear me?
Yeah, sure.
Okay. So thanks, Susan, for inviting me to give a talk on this workshop. So the workshop is longitudinal distribution is learning. So actually, I don't have much studies in this topic, but in my research, that is, I'm mainly work on using machine learning for brain disease diagnosis. So actually, in the brain diseases, there are many problems. So which have the long-tailed data distribution problem. So for example, in practice, you usually have a lot of diseases, but usually we can only get one major data from, for example, in Alzheimer's disease, and there are some other related diseases, but for those diseases we don't have enough data. Okay, so in this talk, I mainly report some recent works on brain disease diagnosis. Okay, so this is the outline of this talk. So first, I will introduce some machine learning methods for brain image segmentation. And then I will report some studies for brain disease diagnosis. So finally, I will report some works for human brain decoding. So in brain studies, brain RRI segmentation is a very important topic, because the labeling, the anatomical structure of human brain is commonly used in the neuroscience studies, but manual labeling is very time-consuming. So there will a great need for automated and accurate labeling method in the brain RRI segmentation. So in brain RRI segmentation, there is a widely commonly used method, that is multi-atlas segmentation. Usually there are two steps. The first one is image registration. So in this step, we will register each atlas image to the target image. In the second step, that is label fusion. So in this step, we will combine the multiple propagated labels from different atlas to obtain the final label. So there is a substitution in label fusion. So that is, if patches of the input image are locally similar to the patches of others, they should have a similar label. So that is a recent very popular method, that is patch-based method. So most of the existing multi-atlas methods, they use image intensity features to calculate the similarity between a pair of image patches for the label fusion. So that is the question: how to characterize the complex patterns of brain MR images. So in our work, we proposed a higher order feature learning for multi-atlas based label fusion. So there are two steps. The first one, we will use a higher order feature extraction step, and then we will route the weight learning. Finally, we will perform the label fusion. So this is the equation for the high order feature learning. So here we use a twice Foley connection and once Foley connection in the learning. So we perform experiments on the elderly data set, and we compared our high order level fusion method is the state of the art for multi-atlas segmentation. For example, LWV, which is the locally weighted voting, and patch-based method PPM, and joint level fusion method, and also the sparse patch-based method. Okay, so we because in the identity data set there are two burnout eyes. That is one is the left hippocampus and the right hippocampus, and here ADI is the dust ratio, and ASD is error. So in both metrics, our method achieve best performance. And this is the visual illustration of the surface distance between the segmentation results of different methods and the ground truth on the hippocampus RI. And this is the segmentation results. Another data set is the Lone LPB40. So in this data set, there are multiple burn regions. So also our method achieves better performance than the compared method. So this is the detailed segmentation results on the 54 RIs achieved by different methods. And also in last year, we also proposed an anatomical attention guided deep network. So for multi-atlas based methods, they have the advantage of using anatomical prior knowledge, but their shortcoming is they only use handcrafted MR features, and also usually the method is very time consuming. And on the other hand, for deep learning network-based methods, they cannot use the anatomical prior knowledge, but their advantages is they can extract texture-oriented features of brain MR images in a data-driven manner. And usually, for those methods, the segmentation speed is very high. So in this work, we can so in this work, we want to combine the advantages from both multi-atlas method and the deep network methods. So this is the architecture of our proposed anatomical attention guided deep networks. So we combine the advantages of both deep learning and multi-atlas methods. We introduce a unique anatomical pattern guided deep learning framework. So this is the detailed architecture for the anatomical gate. And also, we perform experiments on the identity data set. So here we use two baseline. One is the FC network, and another is the UNet network. Both are widely used in the medical image segmentation fields. And AGFC and AGUNet is our proposed method. So here we can see by incorporating the anatomical structure information provided by the atlas to the deep learning framework, we can boost the segmentation performance. And this is the visual illustrations. And we also compare our method with some state-of-the-art methods for multi-atlas segmentation. So we can see our method also perform better than other methods. This is the results for Lone LPB40 data sets. Okay. So from this experiment, we can see our method both have a high segmentation accuracy, and also we can have a very fast speed. For example, for our AGUNet method, see it can segment an image in less than 5 seconds. While for the state-of-the-art method, for example, in the GIF method, they usually use more than 1 hour to segment an image. Okay. And in the second part, I will report the studies using machine learning methods for brain disease diagnosis. So here I briefly introduce some background on the brain disease. So here we mainly focus on Alzheimer's disease, for short is AD. So for AD is the most common form of dementia. And up to now, this disease has no cure. And most often, this disease is diagnosed in people over 65 years of age. And in the world, there are over 40 million sufferers. And it is predicted to affect 1 in 85 people globally by 2050. So in the figure of the left bottom, we can see for AD, there are the 3 different stages. So the left is the normal control. So in this stage, the person is healthy, and then it goes to mild cognitive impairment, for short MCI. So in this stage, MCI is an early stage of AD. So for some MCI people, they will convert to AD in, for example, a half a year or 1 year or 2 years. And for some other MCI people, they want to convert to AD in a very long time. Okay, so for this stage is a very complex stage. And finally, in the third stage is AD. So AD is the final stage. Okay. So this figure shows different biomarkers to diagnose AD. So we can see, for example, we have some imaging-based biomarkers, for example, PET and functional MR, and also we can have some cognitive and clinical functions. So in this figure, from left to right is different stages, from normal preclinical, mild cognitive impairment, and finally dementia. And the white label is the ability to detect the AD. So we can see some imaging-based biomarkers have very high capability to detect AD, especially in the early stage. So this is the motivation. So why we should use the imaging-based biomarkers for AD diagnosis. There are many imaging-based methods to detect the AD diseases, and recently there are some research working on to firstly convert the imaging data to the network, that is brain network, brain connectivity network, and then extract the features from the brain networks. So there is a domain called brain kinetics. So brain kinetics studies the interaction of brain functional regions at system levels. And usually there are three kinds of connectivity. The first one is the structural connectivity. For example, we can get the structural connectivity from DTI image. And another is the functional connectivity. For example, we can get the functional connectivity using the functional MR. And finally is the effective connectivity. So this is a Euro. This is a Euro flowchart for network-based collaboration. So firstly, we construct the brain networks from the neural imaging data, and then we extract the features from the brain networks. Finally, we can perform the classification using machine learning classifications. For example, XVM and deep learning and many other classifiers. So this is a very simple flowchart. And in the early studies, there are the mostly used methods from the graph theory domain. For example, so this work shows a work using the local methods of network. So we first construct the brain connectivity of graphs, and then for each node of the graph, we compute its the local clustering coefficient and use it as features, and then we perform the classification using SVM. So this flow chart is very simple. And in 2014, so we studied using the graph kernel, which is very commonly studied in the machine learning domain. We want to use a graph kernel for brain network classification. So this is the main idea. And in 2018, we further studied this topic because in early work we only use the existing graph kernels, but those graph kernels are only used for example for the Zhang studies, but for brain studies, for brain network, there is some characters. For example, each node in the network corresponds one different or unique brain regions, and each regions have different meaning. So we want to consider the uniqueness of each node in the brain networks. So we proposed a new graph kernel, and we use this new graph kernels for brain network classification. Okay, so we validate our method on the MCI ABS number control classification, and also for the early MSI and the late MSI classification. And both experiments validate our proper methods. And also we can find for the Gaussian brain subnetworks for different groups as in MCI and number control groups. There are different topology in the brain networks. And another topic is how to construct the brain network. For example, we can use the Pearson correlation to construct a functional network from the functional MR. For example, here in this figure, ABC and the different brain regions, and for each region, we compute the average time series for all the voxels in this region, and we perform the Pearson correlation between the average time series, for example, in the region A, and the average time series in the region B, and use the Gaussian coefficient as the weight of the network. But in this method, we usually consider the second order between paired brain regions, and they cannot reflect the higher order relationship among multiple brain regions. So we will study how to solve this problem. So our solution is use a hypergraph. For example, here in the left, this is a simple graph. In the simple graph, for an edge can only connect two nodes. But in the hypergraph, so this is in the colorful hypergraph. So for the hypergraph, there is the node and the habit or habit, it can include more than 2 nodes in this habit. Okay, so this is the flowchart for HAP connectivity network for brain disease diagnosis. So we first construct the connectivity HAP network from the time series, and then we extract features from the HAP networks, and then we perform classification on selected features. Okay, and so this is the results on MCI classification. So here the CNCC is the simple is the results on the simple graph. So for the simple connectivity network, we compute the local clustering coefficient, and for HCC is the method of our purple network HAP network. So we can see for the HAP network based method, the accuracy is greatly improved. Finally, we will combine the 3 kind of features extracted from the HAP graphs. You can get a very high segmentation. You can get a very high classification results. So this is the most discriminative HAP edges, and the HAP edge can be seen a new network biomarkers, and compared with the simple brain region or edges, or the edges, the HAP edge has more powerful ability. Okay. And finally, we also proposed a method to construct the weighted network and directly mine the weighted network. So here we proposed a frequent ordinal pattern. So for example, in this figure, at the middle part, we consider AB and BC. So if the weight of AB is greater than the weight of BC, so we can say ABBC is an ordinal pattern. So this ordinal pattern can use the weight information, and we directly mine the frequent ordinal pattern. Okay, and then use it as the features. So this is the flowchart for using the ordinal pattern for the brain network classification. Okay, so firstly, for each group of diseased people and the normal control groups, we perform the frequent ordinal pattern mining for each groups, and then we perform another discriminative ordinal pattern selection step. Finally, we perform the classification. So this is the classification results on 3 kind of datasets. This is AD, MCI, and ADHD. And here we also use for all the datasets, we use the resting state functional MR, and we firstly construct the brain networks, and then we use our ordinal pattern based method, and also we compare our method with some traditional brain network based classification. So here we can see using the weight information, our method can have a much good results. Okay, so here is the top ordinal patterns identified in the normal control and the AD patients. So we can see the ordinal pattern can also be seen as a new network biomarkers. And we can also study to bring network classification based on the hub detection. For example, in MCI, we can construct a brain network, and for example, in the hippocampus, so this node will be very, very important, and this privilege can be seen as a hub. So we firstly detect these important hub nodes, and then perform brain network classification. Now also we can combine the node level. We can use some network embedding based methods, but due to time limit, if you're interested, please refer to this paper. Okay. And also when we have both structural and functional connectivity, we can combine this structural and functional networks. So here we use a deep learning based network to combine the structural and functional networks for the multimodal classification. Okay. So here we also proposed a multi-layer brain networks. Here we use the coherent network. Okay. And finally, we will introduce using machine learning methods for the human brain decoding. So this is the illustration for the right top figure, and for a subject, we record the functional MRI when a person sees different images. For example, when a person see a shoes, we record his fMRI, and when the person see an image of a cat, we also record his fMRI, and we use the fMRI as input, and the class label shows our cat as the output, so we can train a model. After training, we can test a person. That is, when a person see a new image, we can use the corresponding fMRI to predict whether the person is seeing a cat or seeing a shoe. So this is called the human brain decoding. And there is a big problem for the brain decoding. That is, different subjects will have very different patterns. For example, here for subject 1, we can see if this person sees an image of fish or house. For a subject S, so we can see, so the perceived image of a fish and house are very different from the subject 1. So here we use the functional alignment. So we want to align the different patterns into a common space. So in the common space for subject 1 and subject S, their patterns will be similar. Okay. So this is the main idea. And the hyperalignment is a classical method to this method. So the equation is at this. I think I don't have too much time. Okay, and in 2017, we proposed a method called deep hyperalignment. So this idea is also very simple. We first use a neural network to map the functional data from the fMRI space to a high dimensional space, and in high dimensional space, we perform hyperalignment again. So this is the basic idea. This is the object function. So this is we use a neural network to learn the mapping, the fx theta, and then perform the hyperalignment in a functional space. Okay, and we also perform some experiments using some open datasets. So here for some simple task, so we use the data when a person see some still images, and also some complex task. The person will watch a movie. Okay, and for each task, our method can get the best performance. And also we have some other related works on brain decoding. For example, in last year, we proposed a shared space transfer learning for the multi-site fMRI data sets. Okay, and we also develop I use fMRI toolbox, and we also have and in this software we will have some function, for example, as a feature analysis, model analysis, and visualization. And this software is open source. And finally, we can also perform some visual images reconstruction. That is, when a person sees different images, and instead of decoding, we want to reconstruct what the person is seeing. For example, when a person is seeing some figures, for example 6, 9, these both are images, and we use the corresponding fMRI to reconstruct the images of 6 or 9. And in our recent work, we proposed using the deep learning based method to reconstruct the image. Okay, so this is the talk of today. Okay, thanks.